When an object is approaching you, these are the equations you have to use to calculate what you would actually see. They are all in your lab manual. Now, beta is the velocity expressed as a fraction of the speed of light. So for 95% the speed of light, beta is just the number 0.95. Now, v and x are the actual velocity and position of the object in your frame of reference. And this is what in a standard first year textbook it would be said you observe. However, if the object is approaching you, v approach is what you would actually see. We have to introduce a factor of 1 minus beta on the bottom line. Similarly, d approach is how far away the object appears to be when it's moving. So x is where it actually is, the d approach is where it appears to be. Time dilation is also affected, so there is the standard time dilation formula. If something is coming towards you, we have to again introduce this extra factor of 1 minus beta. And just to remind you, the delta t naught is the time that passes on a clock in its own frame of reference. The delta t approach is the time that you as a stationary observer experience while you see delta t naught pass on that moving clock. Similarly, for an object that is moving away from you, we have to use these equations. Again, v and x are the true velocity and true position of the object. If the object is moving away from you, its apparent velocity is given by v receding, v over 1 plus beta, and it appears to be at that distance, even though it is truly at position x. And when it is receding, we have to modify the time dilation formula with this extra factor of 1 plus beta. And again, the delta t naught is the time that passes on the moving clock. The delta t receding is the time you actually experience whilst you watch that clock receding. So if this factor gamma 1 plus beta works out to be about 6, then if delta t naught was 1 minute passing on the moving clock, while you watch that apparent 1 minute past, you would experience 6 minutes in your frame of reference. Now, in this exercise, you'll resolve the twin paradox by calculating what you as an observer on Earth would actually see and what your travelling twin would actually see on a return journey to Alpha Centauri, 4.2 light years away, at 95% the speed of light. Now, each individual step is relatively simple. The difficulty is deciding which equation applies and which time or which velocity is which. That is the thinking bit. But there are many steps in this calculation. It is very important to preserve at least 6 decimal places of precision at each step to avoid accumulating round-off errors as you work through this exercise.